The problem with comparing directly opposing forces in physics is that they annihilate each other. Take particles and antiparticles, for example. When they meet, they annihilate each other and produce energy as a result, just another form of the same components. To have an actual changed result, you need two forces not directly opposing, but somewhat on an angle. First, for some language. A particle is, broadly speaking, a sliver of matter. Waves are a disturbance moving through a medium. If you drop a rock in a pond, the rock disturbs the water, sending the force out through all directions in the water. Light's a pretty interesting thing, and it can act in weird ways. It can be used to charge a car or to shoot a spacecraft to its destination. However, one of the most interesting things about light is the way it travels. Light exhibits what's called a wave-particle duality, where most of the time it's in a superposition of the two, meaning it's both at the same time. Now let's go into why light can't just be a wave and why it can't just be a particle. Why it can't be a wave. One main property that waves exhibit is the ability to be either constructive or destructive. If you have two identical waves in the exact same spot, their high points, crests, will add together, meaning that the culminant of wave will be larger. The photoelectric effect is the process by which light ejects electrons when it hits the surface. If light's a wave, we should see that the electrons which are ejected should have more energy if we stack light waves, i.e. we make the light brighter, because the light in total should have more energy. So a bright yellow light should have more energy than the dim violet light, right? This, however, is not the case. It just means that more electrons are ejected, but at a lower energy. In fact, no matter what intensity of red light and below, it doesn't have the energy to expel electrons. Even if you had the most powerful red lamp ever created, it still won't expel any electrons. You'll just excite a lot of them. This is like being in a wave pool and having several wave generators going all at the same time, but the waves hitting you are hitting you just as hard as a single wave, but they're just hitting a lot of people. Waves don't act like this. So light must be a particle then. Since bright light doesn't mean higher energy, it just means more of something. A particle. Case closed then, right? Not so easy. Light's wave effects are very apparent. Interference can happen, causing waves to pile up and distort, giving off a mix of colors. This can be seen in a soap bubble, where light waves are constantly messing with each other. The biggest evidence, however, is from the double slit experiment. The light in this experiment visibly interferes with itself. Projected onto a screen, in the section where the troughs and the crests meet, there's no light. However, where the crests and the crests meet, the light is much stronger. Visualizing the waves gives us the locations where the light will be strong and where it'll be weak. If light were a particle, this would be like two pitchers randomly throwing baseballs at a wall. And on the wall, there are several strips where no baseballs have hit. And then directly beside them, there are other strips that have twice the baseball hits that you'd have expected. So if light isn't a particle, and it isn't a wave, then what is it? Well, as anything quantum will do, when it's presented with two doors, it'll pick both. The wave and particle forms create the quantum superposition, also a property possessed by electrons. A superposition is basically when something is in two states at once. Like if you put a speaker onto a motorcycle. You still have the sound from the speaker, but the speed of the motorcycle. Calling the whole thing just a motorcycle or just a speaker is simply not an accurate description. However, calling it a motorcycle with a speaker is. Like particle or wave isn't accurate, but superposition is. Light flows outwards from a point, like a ripple or a sound wave, but it only hits in one spot. The wave determines the probability of finding the photon in a certain spot. Let's say I was baking a wedding cake, and for some reason I accidentally dropped a raisin into the mix. When the wedding cake was all put together, the people with the biggest slices, of course, would have the largest chance of finding the lone raisin. If sound acted like this, and I had a megaphone and yelled out into a crowd of people, the sound wave would expand like a sound wave normally does. However, it would only land in one spot, meaning that only one person could hear me. The weird thing is, though, that whilst traveling, light acts as both a wave and a particle. And as soon as it's observed or measured by anything, it chooses one way to act. This is the reason that light's particle properties and wave properties have been observed in separate experiments, but never at the same time. without touching or interfering in it with any way, just by measuring it, looking at it. Light changes fundamentally what it is. One of the most famous thought experiments of this is Schrodinger's cat. In this thought experiment, Schrodinger describes a cat inside a box with a vial of poison that has a completely undetectable chance of breaking. He states that if we treat this like the way photons act, we have a chance that the cat is alive and a chance the cat is dead. Because of this unpredictability, while we can't see the cat is both alive and dead simultaneously until someone opens the box to see if the cat's alive. The cat remains in both options until we force the universe to choose. This is the way light acts. It acts as both a wave and a particle until we force the universe's hand by observing it. The most bizarre thing about this is that it actually happens. Ordinary light that's been bumping into you every day of your life acts like this. Just by being in the way of a photon, you have fundamentally changed what it is on one of the most basic levels. Light's special in this way. It has two different forces, or more specifically, ways it can act. Instead of them destroying each other, like what normally happens with wars or collisions, light chooses both of these two options. If we go back to particles and antiparticles, when they annihilate and create energy, they create exactly enough energy to make a new particle-antiparticle pair pop into existence. These can then annihilate each other, and then the process repeats, which I believe isn't representative of true change. Waves and particles combine to form the duality. They don't just create another form of the same building blocks. Because they're two different things that show both forms at the same time, they create something that neither of the components can do alone. This, therefore, makes it fundamentally different than its components. What I believe is truly representative of change.